The question starts out by giving us some information about countries A and B, the chances that they'll go to war, the cost of military strength, the value of their military if they don't go to war, and so on and so forth. And in the actual question says, in the Nash equilibrium of the one-shot game, what is the military strength of B? And we're assuming that they're picking their strategies simultaneously. So simultaneously, like we know it, means at the same exact time. Well, it's not necessarily that it's at the exact same time. It's just that player A doesn't know what player B is doing when A makes his choice. So simultaneous here just means that one player doesn't know what the other player is doing when they choose their strategy. Well, first let's write the total value function of each country. I've defined total value as the non-war military functions less expected war losses less military spending. This is what he told us to maximize, so I just wanted to have a name for it, and I called it total value of each country. This is A's total value function, and this is B's total value function. So first let's start from total value of A, and we're going to find A's reaction function. Our reaction function tells us what A will do given a choice of military strength by B. So it's just a line that lets us know how one opponent will react to the other opponent's choice. And the way we find the reaction function is we take the derivative of the total value function with respect to SA and set it equal to 0. So first we can clean this up and plug in 800 for VA, which was given to us in the problem. Now we're ready to take the derivative with respect to SA. The 9.9 SA just becomes 9.9. And now the second part, be careful with this derivative. We have minus 0.01 and 800 all left on the outside of the bracket, so we didn't distribute that through. The inside, the SB times 1 minus SA, well, we can distribute that through, so that'll be SB minus SB times SA. And since we're taking the derivative with respect to SA, the only thing that's left is a negative SB. So make sure you're comfortable with taking that derivative. And the last component becomes negative 40 SA because it was negative 20 SA squared. We set this derivative equal to 0, and we start to simplify, and we see that the reaction function for country A is equal to SA equals 0.2475 plus 0.2 SB. Well, now we can do the same exact process for country B. We plug in 1,000 for VB. This was given to us in the question. We take the derivative with respect to SB, and we start to simplify this down. Again, we're going to find B's reaction function is equal to SB equals 0.2475 plus 0.25 SA. Now that we have both reaction functions, we can use substitution to solve for one variable. So I just chose to substitute in A's reaction function into B's reaction function. So SB is equal to 0.2475 plus 0.25 SA, where SA is equal to 0.2475 plus 0.2 SB. So now I have one variable and I'm able to solve. Doing some algebra, I simplify and I find that SB is equal to 0.3256579. Well, let's look at a graph of these two reaction functions. We see that the graph of these reaction functions lets us know they have positive slopes, so they're upward sloping reaction functions. What does this tell us? This tells us that, a lot of information, it tells us that one country is going to react positively to the choice of the other country. What I mean by that is if B has a really big army, A would like to have a really big army also. So they're not inversely related. They have a positive correlation. Because if A has a really big army, we'd be stupid if we're B to have a really small army. We're really taking a risk. Instead, we want to match that size army, if you will. So not necessarily match, but we want to have a larger army. Well, we see that in a simultaneous move game, this is where we're going to produce, where the two reaction functions cross. So these two yellow dots is where we're going to have our optimal SA and our optimal SB. We found our SB was equal to 0.3256579, and in this question, that's all that we were asked to solve for, and we know that SA star is there, but we're not actually asked to solve for that for the problem set. If we did want to solve for that, we would simply plug in SB into A's reaction function. So we're close to solving for SA. We don't have to in this question, but that's how we would.